Okay. Welcome everybody. Can everybody hear me? Also online?
Yes, we can hear you.
Okay. Can you see the screen?
Yes, we can see the screen.
Okay. Good. So last lecture, we started to talk about some concept on statics and how to map forces from the vector to the joint space, to torques. Then we started to also to introduce the Lagrangian approach that is used as one of the two approaches we'll explain to derive the dynamics of a manipulator composed of a serial chain of rigid bodies that are the links. Lagrangian approach is an energy-based approach. So we were deriving kinetic and potential energy for each link, which means we were deriving kinetic and potential energy for a rigid body at first. And then we were applying the Euler-Lagrange equations to derive the full expression of the model, which is generic for every, this approach is generic for every kind of robot. And we saw that the dynamics of a robot has some terms, inertial terms, Coriolis and centrifugal vector forces, of Coriolis and centrifugal forces, and a vector of gravity forces. And also, of course, a vector of torques. So now we would like to continue with an example. Let me check, because I would like to. Use a presenter view. Okay, this way I can write on the slide. Can you still see the slides?
Yes.
So let's do first a simple example of with a single link and a single joint, a robot with a single link and a single joint, driven from a motor, an electric motor here with some inertia. And we see here that we have the two moments of inertia, Jm and Jl. Jm is the one of the motor, while Jl is the moment of inertia of the load. With respect to what? With respect to the spinning axis, which is this. We call Z, aligned to Z. We see first this simple example, 1 degrees of freedom, and then we compute another example. We will do another example with more degrees of freedom that you will apply Euler-Lagrange equations. So this is nothing more than an actuated pendulum, where we have a motor driving through a gearbox, a load. The gearbox, this is not equal to 1. It's just some reduction that could be 10 or 100, for example. Then we have a mass of the load with the gravity applied on the center of mass, gravity force. We have a distance L from the motor axis, which is this. So this distance L of the center of mass from the motor axis. Then we also have some viscous friction, both at the motor and at the load, Bm and Bl. And we need to remember that the Bm will be motor side, and if we want to map it load side, we need to multiply by the gearbox ratio n. Then we have tau m, the torque at the motor, that is strictly related because the gearbox is not flexible to the torque at the load, again through the gearbox ratio n. Then we have an external force, horizontal one, always horizontal, applied in this point at a distance a from the axis of rotation. Okay, and we can apply both the external force and the torques arbitrarily from the outside. The angular position is of the link is theta L and will be related to the motor position theta M. So in essence, because we have no flexibility, we have 1 degree of freedom only in this system, and we can write the equation either for theta L and then derive them for theta M, or we write for theta M and then we can easily get for free for theta L. So we have only one generalized coordinate, either theta M or theta L, but we for the computation of kinetic energy, we consider both of them in the computation. You will see what we will do. The pendulum is moving in a vertical plane, so we have a contribution of the gravity that is applied at the center of mass of the link, as I said, and it should not be confused with the other external forces, because gravity is not an external force; is intrinsic into the configuration of the system because it's accounted already in the potential energy. So it's considered already in the left-hand side term of the Lagrangian.
Non sapevo che era lezione, se no era 3 minuti.
No problem.
Fino a 7:30?
Sì.
Okay.
So gravity, it's position dependent, is related to potential energy. You cannot change from outside, and the only way to change is through the change in the configuration Q. So it's an intrinsic force and not an external force, while it's a case of tau m and Fx. So we can relate tau m and tau L, theta L and theta m with the gearbox ratio, and also tau m and tau L. This holds at the velocity level, but if you consider, for example, an offset, it holds at the position level. Doesn't matter. We choose to write everything in theta L coordinate. And at first, so we have two bodies in essence. One is the motor that has some inertia, and the other one is the link. But these two bodies they are like a single rigid body, right? So to compute the kinetic energy, we consider the fact that one body it's only rotating, because as the center of mass of the motor is on the axis, because if you have an electrical motor with the center of mass out of the axis, you will have destabilizing vibrations that will break the motor very soon. So only inertia for the Jm for the motor. So we consider only the rotational kinetic energy, that in this case is a scalar because we have only one term in the we are considering rotation only about z axis, so we consider Jm, the moment of inertia about z. And then we have what? We have the link that is rotating, that has its inertia about the center of mass, its center of mass JL, and also we have, since we are rotating an axis, about an axis that is not passing through the center of mass, we need to apply the parallel axis theorem. So we will see here that if we apply the conic theorem that we will do in the other example, this will come for free. Okay, but in this case, we take this approach and we consider the inertia about the z-axis. So the body will be only rotating the link body and at a certain velocity theta L dot, and we'll have a kinetic energy that is this one. So you remember parallel axis theorem, you take the inertia about the central mass, plus you add the, you shift it, in essence, you add the additional part as the body was a particle mass, and you put the distance squared with respect to the axis of the central mass, which is L. So because of this, we no longer need to compute the contribution due to the linear velocity of the central mass of the conic theorem. We only consider the rotational part. Sorry, I closed the door. Okay. And we see that this is equivalent to the moment of the inertia of the body, of the link body around the z-axis. Now, we see the same picture from the side, and we see that the gravity is applied here. We refer everything with respect to the inertial frame aligned with these two axes. And we want to compute the potential energy. So we project the center of mass position onto the gravity direction, considering like the vertical component of the center of mass. So we U0, we have an offset term that we will see how to set it, and we projecting the vertical component about, let's say, the axis, the frame is this one, so it's L cos theta of the P COM vector. So because gravity is vertical, the vertical component is minus G L COM L cos theta, sorry. And this is, yeah, this is defined up to a constant that we will see it will disappear with the differentiation. And we can choose this constant to have the minimum potential energy at 0, which means that the minimum potential energy will be whenever theta is 0, so MGL, so we can choose U0 as MGL. But we will see that this doesn't matter when we apply the Lagrange equation. So if we write the Lagrangian is kinetic energy minus potential energy, so we write whatever we computed before. minus u is plus mgl cos theta minus u0, which is the constant we're talking about. Now we can apply the Lagrange equations. First, we compute the derivative with respect to q dot. We said that our q is theta L. So we compute the derivative with respect to theta L dot, which is, because JL is constant and the 2 nullifies with the 1/2, it becomes JL theta L dot. Then we differentiate again with respect to time, so it becomes JL theta L dot dot. And then we do also the partial derivative with respect to theta L, which is minus, because of the cosine, becomes minus sine, JL sine of theta L. And we see that in the differentiation, the U0 term that is constant disappears. Now we consider the non-conservative forces that are acting on the coordinate theta L, and they are what we have, in your opinion. What are the external forces that we can control from outside? Fx. Okay. Then viscous friction. Which one? Can you tell me the expression? Link side. On the links, on the link side. BL. Good. And the motor side one? So they go with the plus or with the minus? Okay. Then BM. Theta and dot. Okay, we can. No, wait. This is we are load side now. We are writing load side. So this is motor side. So we need to multiply by n to map them load side. And Fx. Then what else? We have the motor that applies a torque. So we have a torque from the motor. Can I write it like this? Okay, link side. Okay, now we have this Fx. We said that we want to, Fx is not acting on the generalized coordinate theta L, is acting on the tip of the link, right? On the, is acting here, while our generalized coordinate is this. So we need to map it into the generalized coordinate. And what we explained last lecture, that is the mapping of a Cartesian force into a generalized coordinate force. Okay, Jacobian transpose. We call it like this. Okay, and we multiply by Fx. And now in the next slide, we will do exactly the following. How to compute this J transpose X. So remember that in static case, you were seeing like tau equal to minus J transpose Fx, the external forces from the environment. But here tau and J transpose Fx are on the same side, so there will be no minus sign. Because they are on the same side, there will be on the other side not zero, but some acceleration. Okay. That's why in statics we had opposite sign, because is like acceleration times inertia equal to tau plus J transpose Fx. Since acceleration is 0 in statics, we have no motion, we put tau on the other side and we add the minus sign. But usually we see tau and J transpose Fx with the same sign on the right hand side. And so we write the position of the central mass, sorry, of the link tip, let's call it X. And it was at, was like something like this, right? It was like theta, this is a length of A. So, and we are interested into the into horizontal component. So, sorry, on the, we get the position of Px is A cosine of theta. We will see that the Jacobian is nothing else that the lever arm to map this Fx into a torque around the axis. Okay, this is the link. And so if we differentiate Px dot, we have a, sorry, this was, sorry, I made a mistake. This is theta, this is L cosine of theta, this is L sine of theta. Okay, if we differentiate A sine of theta, we got L cosine of theta, theta dot. Okay. And this is the Jacobian X that maps velocity at this point into, so joint velocity theta L into Cartesian velocity of point X in the X direction, while the transpose, it will be, since it's a scalar, will be the same thing. So this will also be Jx transpose. And we can account for that into the U expression. We collect theta L this time. Sorry, in the previous slide, I forgot to multiply also by n squared, because we need to map link side, we need to compute the link velocity, but also since is a force, is a torque, you need to multiply also the torque. So this will come n squared plus the famous Jacobian transpose this way. Okay, so if we compute the Lagrange equations, we need to do the dt, put everything together, all the terms we computed, and we get JL theta L dot plus MGL sine of theta L equal to n tau m minus friction on the load side plus friction on the motor side mapped to the link side, to the load side, times the velocity, which is a velocity dependent force, plus a cosine of theta L fx. Okay. Okay. Then this is the model, and we can express this model also equivalently in the variable theta m, but just setting divided by n and replacing theta m, removing the theta m here. Sorry, the n from the tau m multiplication. So we can get very similar expression, and we get this equation, which is a differential equation, second order, that needs to be integrated because we have a relationship between forces and acceleration. So we can get the acceleration out of that, and we need to integrate the differential equation. So if we write a block diagram, in essence, we get the torque here that is divided by n is sorry, this should be multiplied by n. We have the friction force here. We have the this is the MGL sine of theta. It's the gravity vector, in essence, the gravity force that is configuration dependent from theta. Then we divide for the inertia at the link. We get the acceleration. We integrate it. We get the velocity that we multiply for the viscous friction term, and then we integrate again. And we get the position. With the position, we can compute the term that is the time varying gain that is multiplying the external force that will feed in again as an additional input. We can simulate this in MATLAB, and since it's a second order system, we know that we have integrators, and we have two integrators that have states, and this means that the states of this integrator should be initialized, and it should be initialized with the initial value for the position, angular position and angular velocity of the link. Okay. Now let's try to use this formula, this model, for example, to do inverse dynamics. So we said that direct dynamics, you compute the motion given the forces. Here, given the motion, we want to compute the forces. And we will see that we call this approach computed torque because we don't use we use the desired motion. We use desired values for the acceleration and velocity and position, and not the actual values. So if we want to give a reference defined in a sampled way or with a time profile, let's say, is a set of a vector of points where you have desired position, desired velocity, and desired acceleration. Okay, and this is for a whole profile time interval between 0 and t. Then let's say our desired trajectory is sinusoidal with amplitude A and angular frequency omega. If we want to also define the velocity, we want to be consistent, so we need to do the derivative of this to avoid inconsistencies, and it becomes cosine of omega t times the argument, which is omega. It multiplies t. Then same for the acceleration. I don't understand Why has some issues? Doesn't write anymore. Anyway, that's part of the screen should have some issues. I'll write it here. So this is the derivative of the velocity, and we go back to a sinusoid. And if you want to be consistent, you want also that the initial state is consistent. So if you have an initial state of 0, the velocity at 0 should be consistent with that. And it should be, if we want to have this, we should be starting not from 0, from a omega. Otherwise, you will have tracking error at velocity in the very initial time. Then we have the input fx and the input tau. At first we start to think that we have no external input fx, so we want to achieve the motion only with tau, the desired motion that we want, the sinusoidal one. So in essence, we invert the dynamic model and we compute the tau m this way. Sorry. So in essence, we plug in velocity, acceleration, and position of a desired trajectory. We compute a profile of torque to achieve that motion, just using the model. Then we can also do the other way around. We set the other input tau m to 0, and we compute the profile of fx to achieve that motion. And we see here that we have one problem, because in essence, this is between brackets is this part here. But we divide for cosine of theta L. And cosine of theta L can go to 0 if you have theta equal to pi half, for example, plus minus pi half. And this is actually making this fx going to infinity, and actually is a point that we call a dynamic singularity, which means that the force fx is aligned with the link, and is not able to apply realize any motion on the link, because it's just in singularity, dynamic singularity. We call this kind of situation. Okay, and this is a typical problem of Cartesian control. That's why we need to be careful whenever we do Cartesian control, because of these problems. While if we consider both inputs, the solution is no longer unique, and we can distribute the effort among the two inputs via a pseudo inversion. So both inputs are present. There is one equation in two unknowns. Okay, we have theta m, tau m, and fx, and in between brackets is whatever was in our previous expression. And then plug-in number, you have a matrix of number here. And then via pseudo inversion, you can compute the values of the tau m and fx that are performing the motion. Okay, this is a simple example. 1 degrees of freedom where we compute the forward dynamics, the inverse dynamics, and we try to realize some motion. And of course, if we don't know fx, or if we know fx, we can compute tau m considering the time profile of fx. So to perform the motion and also counteract the influence of fx. But now we want to do something more complex, and we want to go from the 1 degrees of freedom example to the 2 degrees of freedom one. And we want to do this for a robot that is not the usual 2R robot, but is a PR robot, so with a prismatic joint in a revolute one. And we see that we can learn a lot of things from that. We want to, it's an hybrid situation with these two nature of joints. We want to compute the kinetic energy. We want to extract the inertia matrix. And then we see that from the inertia matrix column, we can do, doing partial derivatives, generate velocity terms with the Christoffel symbols that are quadratic in velocity. And these are Coriolis and centrifugal forces. Then we can also compute the potential energy, extract the gradient, and get the gravity torques, and compute the model, complete the model of the robot. We will see this. So we have two links and two joints. So 2 degrees of freedom. We consider the horizontal plane. So gravity is always perpendicular to the motion of the links. So it's doing no work. This means the potential energy is constant and its derivative is 0. So the gravity vector will be 0 on the horizontal plane. Now we need to compute. We have two joints. One is it's moving linearly along this x-axis. Not here. We are not using our usual convention, just for convenience, because you will see it's becoming much easier this way. So the joint is not the z-axis along which the joint is moving, but is the x-axis. Then we have a rotational joint that is moving around this axis here. And the position of central mass, we could define about this, but we define about this point, doesn't matter. It's just a constant position with respect to the link. In this case, this point of the link. And the other central mass is again referred to this point as a fixed position DC2. So if we want to write express the position vector of the central mass of link 1, PC1, expressed in the YX frame, YXZ frame, we see that PC1 only moves along the x-axis because we have a prismatic joint, and is Q1 minus DC1. While no motion is on the y-axis, so remains at 0, and also on the z-axis, which is coming out from the paper. Then we can compute the potential energy of link 1, considering that this link is only translating. So if you apply Koenig theorem, we have only the component of kinetic energy due to the linear motion, which is 1 VC1 transpose VC1, where VC1 is the time derivative of PC1. So is Q1 dot 0, 0, because this is constant, so the derivative is 0. And so if we do 1/2 M1 Q1 dot 0, 0, which is the transpose of the VC1, Q1, 0, 0, we get what? 1/2 Q1 dot square. Okay, very simple. Now we compute the PC2, the position of center of mass of link 2. We have the contribution due to the motion of link 1, plus we have yeah, here we didn't okay, Q1 is the motion of this point of the link 1, so we refer to this. So this is the position of PC2 is Q1 plus DC2 cosine of Q2 on the X direction, this term plus this term. While on the Y direction is DC2 sine of Q2, because this part, and 0 on the Z direction. And if you compute the VC2, the velocity, doing the time derivative, we get Q1 dot minus DC2 sine of Q2 dot, and on the Y direction we have DC2 cosine of Q2 dot, and 0. Okay, then what about this link? This link is only translating. Surely is translating because of the motion of the previous joint, but this link is also rotating. So we need to compute for the Koenig theorem also the value of the omega vector for this link, omega 2. And what is the expression of this omega vector? What coordinate does it have? So this link is
0, 0
to Q dot. Q2 dot. Very good. Okay. So as one axis align it's a vector aligned with the z axis, so that with magnitude Q dot, Q2 dot. Okay. Now we can put everything together. What we have, we compute the kinetic energy for the second link that will have the translational part with the linear velocity and the rotational part with the angular velocity. Here we need to put the tensor of inertia about the center of mass of link 2. Okay. Now you will see that if we put omega in a quadratic form, and the omega has the first two elements equal to 0 and the third one not, you will see that you will get out something like that. This number squared times the component free, I, z, z. Okay. You can do the computation and verify this. While the other two terms are just the square of the coordinates of a velocity vector, and we can compute them. It was Q1 dot squared plus DC2 squared. You see that you get some simplification, because sine squared and cosine squared is going to 1, and then you have the double product of the first coordinate of VC1, that is VC2 sine of Q2 Q1 dot Q2 dot plus whatever we say that was Q2 dot. So we express this term IZZ. So this becomes a scalar because the energy is a scalar. So we have IZZ Q2 dot squared, quadratic form that becomes like this. And if we put everything together, we also add the previous link. So M1P1 squared plus we write all this. EC2 sine of Q2, Q1 dot Q2 dot plus is missing 1/2. Okay, now we see that we can compute the inertia matrix from the kinetic energy. In several ways. One way is to extract the parameters from the quadratic form of the kinetic energy. So if we look at the kinetic energy quadratic form, we in essence we have the kinetic energy is 1/2 Q dot square M Q dot, where M is the mass matrix, and we see that if we do this explicitly, this product, and you work out with the multiplication, so you multiply this column for this and this column for this, and you get these two elements, and then you multiply again for the Q1 Q2 dot vector, then you get something, this quadratic expression. We know that the inertia matrix is symmetric, so M21 is equal to M12, the off-diagonal term, and we can extract directly from the kinetic energy expression. If you look at the term, we can extract the value of the mass matrix, entry of the mass matrix, of the inertia matrix, sorry. And in this case, we see here we have the one that multiplies Q1 squared dot, Q1 dot squared are these two. This other one is multiplying Q2 dot square, and we have a mixed term here. This other one is multiplying Q2 dot square. And we can factor out the entry of the inertia matrix in the next slide. Alternatively, you can use the expression that we will use in another example with the Jacobians. Okay, there is no, it's your choice. If the problem is easy, maybe it's convenient to do this way. So you get the entry M11 that multiply Q1 dot squared, M22 is multiplying Q2 dot squared, while the mixed term are related to the M12 or M21 entry. And if you do that, you see that you have the mass matrix, that there's this expression. This is the first column, this is second column. And you see that you have on this upper left, you have the masses of the link. You have the inertia only appearing in this lower right term, the inertia of the second link. And to compute the Coriolis term, you apply this formula. First, you compute the Christoffel symbol for that coordinates. So we start with the first coordinate. And we do the differentiation of the first column of the matrix, of the inertial matrix, which is this one, with respect to Q variable. So we get first this term with respect to Q1, we see that is constant, so is derivative 0. Then we do differentiation of this term with respect to Q1. Again, is only dependent on Q2, so it's 0. Then we do differentiation with respect to Q2, is constant, so it's also 0. And whenever we differentiate this one with respect to Q2, we have something that is non-zero, which is M2 dC2 cosine of Q2. Okay, very good. We said here we need to sum the transpose of this. The transpose is exactly the same. Minus what? Minus this is the derivative of the mass matrix, of the whole mass matrix, with respect to the Q1 variable. So we are considering first Q1 variable. So we differentiate this term by Q1 is 0. This term by Q1 again is 0. This term by Q1 is only dependent on Q2, so it's 0. And this one again is constant and derivative is 0. So we get in essence 1/2 0 0 0 minus 2 m dc2 cosine of Q2. And this is to compute the C1 element. Here we do Q1 dot Q2 dot the C1 element, which is this one, times this. And we see that since this is the only non-zero term, we will have this multiplied by the entry Q2 dot squared. The 2 goes away because it goes away with the 1/2. So this is the first coordinate of the Coriolis centrifugal vector. We see that we don't have any Coriolis here. We have only something that is quadratic in the joint velocity, and it is this is only a centrifugal term. While for the other one, we take a second column. We do the same trick. I don't know if you want me to do that. In essence, the first column is this one. Again, no, sorry, this time we consider the second column, and the second column we differentiate with respect to the Q1 variable that is independent from Q1, so we have 0, 0. And if we differentiate with respect to the Q2 variable, the first term as the derivative of this times this is a scalar, so M2 dC2 cosine of Q2. And this again is constant, is dependent on the Q2 variable, so you have a 0 here. This time, if you transpose it, you get this, you get it to here. And if you do the derivative of the mass matrix with respect to the Q2 variable that we are considering, applying the formula, you get the term, constant term, which is independent, both of them. And these two are this time dependent on Q2, so you can differentiate and you get the same thing as before. So if you sum up this, you see that C2 is a matrix of 0 because this summed up to this minus this is getting 0. So the second component of a Coriolis term is 0. Coriolis centrifugal. Okay, this is, we will see, we will analyze afterwards this more in detail. And then putting everything together, we have the inertia matrix here and the Coriolis centrifugal vector and the vector of torques, which can be tau 1, tau 2. You can specialize. And this is the dynamic model of this PR robot manipulator, where we concisely name the inertia matrix with M of Q, Y of Q, function of Q, because we have a dependency on Q2. So we have a dependency on position, even though these terms are constant, we have some dependencies. And here also we have a dependency on position, but also dependency on the velocity, on Q dot, okay? Then we can do some observations here. As we said, this term is constant, the lower bottom right term. And accidentally, in this example, also also this term is constant, but generally is not. While this term here is constant for every kind of robot. It's not configuration dependent. And this is because represents the inertia of the last link, of the last joint when moving the last joint. So the inertia seen by the last joint whenever this joint is moving, and whatever is attached to the very last joint is just the last link, and the last link is a rigid body, so its inertia is not changing in the configuration. But instead, if you consider the first joint and you move the second joint, you will see that the inertia changes because the second link is moving and locating itself in a different position with respect to the first. Okay. The second observation you can do is that that the inertia is never for all the robot a function of the first joint coordinate of Q1. Why? Because if it was function of Qy, it would mean that you have an inertia that depends on the choice of the first reference frame. So if you locate the 0 frame here, you have Q1, you remember, you will start, I don't know, this position will correspond to 60 degrees. If you put it like here, will be 90 degrees. So it means that you would have an inertia that has different values if you locate differently the initial frames. And this is not possible because it's a physical property. Then we have why we don't have Coriolis term, only centrifugal, because yeah, the centrifugal terms are the ones, remember that sorry, the Coriolis term are the ones that have mixed product of Q1 and Q2 dot, because we have a prismatic joint at the beginning, so there is no rotation. The second joint is to have Coriolis forces should be moving linearly on a rotating while rotating. So since the first joint is just prismatic, is not performing any rotation, there is no Coriolis force. The last comment is about the centrifugal contribution that we saw that is due in the first joint is present and is due to the motion of joint 2. So there is never a centrifugal contribution of a joint on itself. We will see why. So the contribution of centrifugal force, it was on joint 1 and it was due to the motion of joint 2, not to the motion of joint 1. Now, if we want to do the inverse dynamics or computed torque in this case, for this kind of robot, let's say this time we want to define a constant position for the first joint. So we have Q1 variable equal to K is a constant, then the velocity will be identically 0 and the acceleration will be 0. The second one, instead, we rotate at a constant angular velocity alpha. Sorry. So this is the angular position. The constant angular velocity is alpha, and the acceleration, because the velocity is constant, will be 0. 0 acceleration means 0 inertial forces. So I expect not to have inertial forces. But let's not forget about initial values to initialize the integrators, and it should be QD 1 and 0. Sorry, this is the actual value. Should be equal to K, and at 0, Q2 should be equal to 0. Then what is the torque that we need to apply to the joints or the force to realize this motion? We plug in this in the dynamic equation. We have no inertial forces, and we see that we have only the centrifugal forces, cosine of alpha t times q2 dot square, that is alpha dot square, and we have 0 for a second joint. And what is this? So now you need to think about joint 1 is still here, and then joint 2 rotates. Boom, 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 boom. Okay. What is the force that joint 1 should do to stay still? It needs to counteract what? They need to compensate the centrifugal force due to the rotation of joint 2, right? Which is exactly this one. So joint 2 rotates, creates a coupling, creates a force on joint 1, and joint 1 needs to counteract to remain, to don't avoid to have any acceleration, because we are requiring to be in constant position. And so this is the force of joint 1 to compensate centrifugal force due to rotation of joint 2. And we said that we have no inertial effect because the acceleration is 0. Now let's see another example of motion where we keep the second joint still at 90 degrees and we apply a sinusoidal motion to the first joint. And this sinusoidal is like this, is going back, going back. So as this formula, which is cosine of omega t. So it's always positive, starts from here and goes to 2a and goes back. And the derivative is a omega sine of omega t, and the acceleration is a omega squared cosine of omega t. For Q2, we want to stay still at 90 degrees, and stay still means that velocity and acceleration are identically zero. Now, if you apply again the model and we want to compute the torque to achieve this motion, we find that we so you remember the model, how was that? So this time Q desired dot is zero, so this term is always zero, and we have only the inertial term. And the inertial term, we need to compute them function of Q2 variable, which is constant. And therefore, and we need to multiply the inertial terms times the acceleration of Q1 and Q2. Q2 is equal to 0. So let's write explicitly what we had. Sine of Q2, how much is that? Is sine of Q2 is sine of pi half. Okay, which is 1. So we can replace. We have m2 dc2 sine 1 of Q2, which is 1, and then we have the EC2ZZ plus M2 DC2 squared multiplied by A omega squared cosine of omega t n of 0. So if we compute them, this time this time this, we get m1 plus m2 a omega squared cosine of omega t, and this for this, m2 dc2 a omega squared cosine of omega t. Okay, we see there is something very similar here in both torques. And so what can we say about this? This is a force because a prismatic joint will have a sinusoidal shape, and in essence is the force that is needed to accelerate the joint one to achieve this motion, okay? And has the same sign, the acceleration as the same, the torque is the same sign of the acceleration. Because we want to move that joint. While this one has an opposite sign with respect to the motion, and is what? Is the torque needed from joint 2 to keep it straight while joint 1 is moving. So it's the torque needed to compensate the coupling, the inertial coupling from joint 1. So if you think about joint 1 is moving like this, which is a positive acceleration for joint 1, joint 2 will move like this. So we'll have to remain at 90 degrees, we will have to apply a counterclockwise torque, so a negative torque. If joint 1 is moving like this, negative force, negative cosine, let's say, then the joint 2 will tend to move this way. Sorry. If joint 1 is moving this way, joint 2 will move this way, and we'll have to do an opposite torque, which will be positive because the force is negative, to keep the Q2 at 90 degrees. So this is torque needed to keep Q2 at pi half and compensate coupling from Q1. Okay, we will see in the control lecture, the last one, that this coupling can be eliminated through a control approach that is feedback linearization. Okay, we can do a short break now of 10 minutes, and then we continue with the next part on this, analyzing this inertial coupling and Coriolis and gravity terms with incremental examples for different kind of joints. Okay, let's start again. I have a quick question. How many of you wants to do the exam online mandatorily? Or how many of you, would you all agree if we do the exam in presence, or somebody of you want to do online? Because I personally don't like to do the exam online, but what I'd like even less is to do something hybrid. So I was thinking to do it online because some of you might want to do it online, but if all of you are available to do it in presence, then we can think about doing it. You prefer in presence?
But the exam is written.
Yeah, the exam is written. In the end, most of you were having this preference of doing it the option one with written or open question, exercise, and quiz questions. And I was thinking now that it's nicer to do it in presence, but we don't want to deal with something hybrid. You know, some people are online and some people in presence. So I will do that in presence if all of you are available to do that. At least in the first the day is the 7th of June. So we will make, maybe we can do another doodle for that, and we will see if everybody of you is available, then we can think about doing in presence. So let's continue. In this part, we will analyze the dynamic equation, having some qualitative and quantitative idea of how these terms look like in different cases. So let's start first considering the case. So let's quickly recap the meaning of these terms. So you need to think about the MKK entry of the inertia matrix as the inertia seen at joint K whenever you accelerate only joint K. But accelerating joint K, it means that we'll move also all the links that are attached to joint after joint K's in the kinematic chain. And because the inertia matrix is positive determinate, the acceleration will have the same sign of the torque. So we enter with a torque, we multiply by MKK, and we obtain the acceleration that is of joint K. So instead, the MKI, which is whenever I is different than K, are the off-diagonal terms of the inertia matrix, while the MKK are the terms that are on the diagonal of the inertia matrix. And the MKI term represents the inertia coupling between the acceleration of the joint I and the torque applied to joint K. So if you apply a torque to the first joint, also the second joint will move. And how will move? It, even if you don't apply any torque to the second joint will move. And the way it will move is determined by this coupled M1-2 term. And instead, the Coriolis term, you need to go back to the equation, the scalar version of the equation of the dynamic model that we did last time. And the CKII, it's represents a centrifugal force at joint K whenever joint I moves, while the CKIJ is the Coriolis force at joint K whenever both joint I and J are moving. And you remember we need to have two joints moving, two rotational joints, we will see, moving at the same time to have Coriolis force. And this force can be affecting all other joints that are before that joints in the kinematic chain. But let's start simple with a 2 degrees of freedom kinematic manipulator that is on the plane, so we have no gravity. We have prismatic joints that are at 90 degrees. So our vector of general coordinate is p-dimensional, and this is the schematic of the kinematics of this very simple robot. Okay. To compute inertia matrix, this time we want to apply the formula that we explained last lecture with the Jacobians. So we compute the Jacobian linear and angular for the points that are at the center of mass of the two links. So J lin 1, you remember we have the contribution of the first joint and zeros for the link after this. And since we are talking about a rotational, a prismatic joint, then and the axis of the first joint is usually aligned, Z1 is aligned with this, with the joint axis, according to our convention, then we will have 001 as Jacobian, geometric Jacobian related to the prismatic joint. You remember the lecture of Octavio, and then we put zeros for the joints that are after that will not affect the motion of this point. So this motion of this point will not affected by the motion of this joint, but only by the motion of this joint. That's why we have zeros. Then instead, if we consider the linear Jacobian of second link, want to compute Jacobian this point, we will have the influence both of the first link, sorry, of the first joint and on the second joint. And this is again the motion of this point is due to the motion, linear motion of this joint, so is 001, you remember Z1, and the axis Z2 according to our convention is horizontal, but we need to remember we need to write everything in the zero frame, so it will correspond and align with the x-axis. So it will be something like this, and this is contribution of joint 1 to the linear velocity of COM of link 2. And what about the J-ang, the angular, the Jacobian related to the omega? There is no rotational motion, so both the Jacobian are 0, are zero column for the two links. And we don't consider them in our computation of the inertial matrix. Okay, then we can use the generic formula we introduced last time, which is J ln 1 transpose J ln 1 times M1 plus M2 J ln 2 transpose J ln 2. And if replace that, so maybe I wrote that, okay, so I don't have to do that. We get something like this. We get what? We get a diagonal inertial matrix that is also constant, so it's not dependent on time. And also, because we have prismatic joint, we will see that if you compute the Christoffel symbols, because you do the derivatives of the column of the inertial matrix, since the inertial matrix is constant, these derivatives will be zero. And so there's no dependency on Q1 and Q2. And so the Coriolis effects and centrifugal effect are zero for prismatic joint. So Coriolis and centrifugal only we will see that when there are rotational joints. We put everything together. This is the model. We have no gravity terms, so we have because we are on the horizontal plane. And instead of torques, we have forces here because we are talking about prismatic joints. Because the matrix is diagonal, whenever you give a force to the first joint, only the first joint will accelerate. Whenever you give a force to the second joint, only the second joint will accelerate. So there are no inertial coupling. And the nice thing is that joint 1 will see what? The inertia, because it needs to move both link 1 and link 2. So we'll see the mass of link 1 M1 and then the mass of link 2, while joint 2 that has to move only the link 2 will see only the inertia of mass M2. Now let's do it a little bit more complex. First let's compute the. Let's consider the case whenever we are in the vertical plane. So we have the effect of gravity that is not zero, and gravity is applied to the center of mass of link 1 and link 2. And you remember, to compute gravity, we need to first compute the potential energy, and to compute potential energy, we need the position of the center of masses. So this was z-axis. This was x-axis. The position center of mass 1 is zero component. Sorry, z was here. On the x, 0 on the y, and q1 plus the constant value with respect to the joint frame that express the position of the the position of the center of mass with respect to the link 1 frame that moves with the joint 1 frame. In PC2, it's the same thing. We have the position of this point with respect to the link one frame, which is fixed. So we have on the Z direction, we have Q1 plus this fixed position. Then we have 0 on the Y, and this time we have something on the x-axis, which is Q2 plus the constant position with respect to the joint frame. Let's say it's here. The link frame is here and it's moving out. And if we compute U, we apply the formula. Potential energy is M1 G0 transpose PC1 minus M2 G0 transpose PC2, and G0, how it does look like, is 0, 0 minus G, pointing downwards in the Z coordinate. And if we replace this here and this here, the minus sign goes away with the sign of G, and we get M1 G, this is a scalar G, Q1 plus DC1 plus M2 G Q1, sorry, that's an error here, Q2, no, it's Q1, sorry, because we get only the third component, because projecting onto gravity, since gravity has only the Z component, we get multiplied only the Z component. So this is something like this. And if we differentiate, we get the gravity vector, the partial derivative with respect to Q. So the partial derivative with respect to Q1, this is a constant, so goes away in the differentiation. And then you get M1G plus the other term, 2G, while the differentiation with respect to Q2 is not, there is no dependency on Q2, so is 0. In fact, the motion of Q2 of this joint, it's horizontal, and the second joint doesn't have to counteract any gravity force, because the gravity goes on the structure, okay, not through the joint. So this is, well, the first joint needs to support both the masses of the two links. Okay. We could have some specific peculiar configurations where the zero gravity, the gravity vector is nullified. For example, think about a robot that has one joint like this and the other joint folded up. Okay. This is like the first joint gravity force is going through the axis of the joint, so it generates no torque, while the second rotational joint is folded up again and is in equilibrium with the structure, and there is no gravity vector different than 0. Is in balance. Everything is in balance. Okay, then let's do something more difficult. And we see that if we don't put the axis of a prismatic joint at 90 degrees, we start to have a dense inertia matrix. So before was diagonal. Now we see that some off-diagonal terms appear. They are equal because matrix is symmetric, but the inertia matrix still is constant. And this represents whatever we call the inertial coupling. that represent the motion of a joint that is affecting the other joint. So this is, as we said, inertial effect of joint 2 on joint 1. Here we are again on the horizontal plane, so there is no gravity, otherwise you would have gravity as well. So what does it mean? That if you, for example, move joint 1, right, you expect joint 2, if there is no force on that joint, to move, right? Because there is inertia. The center of mass is there. You start to move up this joint, and you expect this joint to go inside. While with revolute joints, let's think we have again the 2R robot with revolute joints. We have AI as the link lengths, A1, A2. Li are the distance of the center of masses with respect to the joint axis. And Ji is the moment of inertia around the axis passing through the center of mass of link I. So this is J1 and J2. Pay attention not to confuse with the Jacobian, because now as generalized coordinate you have theta 1 and theta 2 as usual, and to compute the Jacobians we need the following vectors. We need the position of center of mass 1, which is L1 cosine of 1, L1 sine of 1, sine of theta 1. Then the position of center of mass 2, which is A1 cosine of theta 1 plus L2, which is this segment, L2, sorry, cosine of theta 1 plus theta 2. And the same for the y component. We have the sine as usual, and since it's moving on a xy plane, we have no z component. We want also to get the position of point 1. This is point 1 to compute the Jacobian. That is A1 cosine of 1, A1 sine of 1, 0. Then both the z1 axis and 2 axis are equal to the aligned with the 0 axis and are vertical. Then for link 1, we have J lin 1. We have rotational joints. You remember we consider only the joints before the link you are considering, and 0 is the other. And the joint that is before this driving link 1 is joint 1 that has Z1 cross the vector going from link 1 frame and the center of mass of first link. So link 1 frame is link frame frame 1. Link 1 frame is here, is whatever is located the 0 frame, so we can put 0 here, and we have a column of zeros, 3 zeros in here, and this P0 is just 0, 0, 0. So if you do the cross product of this vector times PC1, this vector, you can see, there was a 0 here missing, you can get this expression L1 cosine of 1 and 0 plus the second columns of zeros. Okay, then for the linear Jacobian, that this time we have rotational joint, so sorry, the angular Jacobian, we have rotational joint, so we have rotational motion, so we need to consider that. 1 and zeros. We have just, remember, for rotational joints, we consider the axis in the 0 frame, and this is 0, 0, 1, and a column of zeros. Okay. Then for link 2, we do the same thing. J link 2, JPC2, okay. Central mass of link 2. We want to compute the Jacobian that links the joint velocities of joint 1 and joint 2 to the velocity of central mass of link 2. And because we are talking about rotational joints, sorry, this is the yeah. So we consider the axis coincident there as before. This time we have a position of central mass of link 2, and then we consider the joint sorry, Octavio, this should be Z2, right? And this is Z1. By the way,
Let me see. Yes, I think that it's correct like this.
okay. Okay, yeah, this is so what I call P1 is not P1, but is P2, because related to link 2, right?
Yes.
And this is equal to P1. So this is P1, P0, and this is P2. Okay, yeah, sorry about that. Because people are using many different conventions, so sometimes we get confusion. And if we do the computation of this, we get A1 S1 minus L2 S1 2, A1 C1 plus L2 cosine 1 2 0, while for the second cross product we get 2 cosine 1 of 2 0. Okay, then if we use this in the formula we presented, we have both the linear Jacobian for the two links and the angular Jacobian. And for the angular Jacobian, you need to left and right multiply for, sorry, this not transpose, the inertia tensor, and the inertia tensor will be something like this. So a diagonal matrix where we consider the moment of inertia about the axis of rotation of a link, because we are rotating around the only around the z-axis. So you will see, if you work out the quadratic form, sorry, if you work out this matrix product, you will have only this term appearing, and the same for the second tensor of inertia. You will see I prepared an example in MATLAB that you can try with this, exactly this computation. You will see by yourself in a symbolic way that the result you get is something like this. So the inertia matrix will have M11 term, which is this, and you see that we have both the inertia of the first link and of the second link, plus the mass of the first link and the mass of the second link. You have dependency on Q2, not on Q1, as we said. And you remember the previous example that was constant, and now is no longer constant. This is a dependency of Q2, while the M22 term is constant. It only depends on the inertia of the link 2, because the link 2, the joint 2 is only seeing inertia of link 2, and this is kind of the parallel axis theorem from, this is the inertia about the center of mass plus the distribution with respect to the joint axis of link 2, and the mixed term of diagonal is again as this shape and as a dependency on Q2. I represent the inertial coupling. Okay. Very good. We can do some analysis, very qualitative. This is what we just said. This term is constant, matrix is symmetric, positive definite, all the eigenvalues are bigger than 0. It's configuration dependent, but dependent only on Q2. And we see that if you analyze the inertia M11, we see that as a maximum, whenever the arm is completely extended in this case, because the inertia is bigger, we said that the inertia is a qualitatively a measure of the distribution of the masses far from the axis, around the axis, and is bigger if you are far from the axis. So if you extend completely the arm, you will have that center of mass is more far away from the axis of joint 1. So you have bigger inertia, while if it's completely folded, you will have the minimum inertia. While in the other case, the coupling term, we see that again, the influence is the biggest one if you move joint 2 with respect to joint 1 when the arm is completely extended. And to analyze its value, we can do a computation. You can find again in another file that is computing the inertia M12 according to the position of the joint Q2, and you will see that it will reduce with a cosine in according to the Q2 angle. Then, regarding gravity torques, this time we have the gravity along the y-axis. So you remember we can have, because we use the G0 vector, we can attach the robot in whatever place. And this time I located the zero frame with the gravity vector along the y-axis direction. And to compute the potential energy, again, we apply the formula G0 transpose PC1 minus M2 G0 transpose BC2. And if you remember, the y component of PC1 was L1 S1, while the minus sign goes away because of the G. Same way, this is a scalar G. No, this is a vector. And the y component of PC2, because we are projecting along the y component, the gravity vector that lies on the y component, it's A1 S1 plus L2 S1 2. And if we do the partial derivative, we get the two component of the gravity vector, which is M1 G. We have a dependency on Q1 here, theta 1, let's say, S1, sorry, cosine of 1, plus dependency on theta 1 or Q1 is both here and here, so we have L2 G A1 C1 plus L2 C12, while the second component of the gravity vector is the partial derivative with respect to Q2, and this time Q2 only appears in here, so we get M2G L2 C12. Okay, and this is the gravity vector. Do you have any question? Everything's clear? Now the Coriolis centrifugal forces, vector forces, is we do just a qualitative analysis here. You can find the expression. I will report the final expression that you can find the derivation in Siciliano book. But what it's interesting is to understand what are these forces. So think about, for example, again, we said that these forces, they only appear, they are fictitious forces. They only exist whenever we have rotational joints. And think about rotating joint 2. You will move link 2, and you will have that, sorry, this is joint, an effect on joint. We check the effect on joint 1 and 2. And we see that if you are rotating, you have a centrifugal force that is along the axis. So it will have no influence on joint 2, on the torques on joint 2. We'll have no torque, will create no torque on joint 2, but we'll have an influence because of this component on joint 1. Okay. And this influence is maximum whenever this is at 90 degrees, because you don't have to do the projections here. It goes all the force, centrifugal force goes into torque tau 1. And there is never influence on tau 2. And you remember before I told you that this fact I would have explained that there is no influence on the joint itself. Then rotation of link 1, check the effect on joint 2, and joint 1 and joint 2. In this case, link 1 is moving, so we have centrifugal force to the center of mass of link 1 and to the center of mass for link 2. we see here this one is not creating any torque on tau 1. This one is not creating any torque on tau 1, but it is creating a torque on tau 2. So we have an effect, no effect on tau 1 and influence on tau 2. So you see, you have always an opposite effect. If you're moving one joint, you see the effect on the other one. While for the Coriolis, they are related to the change of what? Of tangential velocity whenever the distance from the rotation axis changes. So if you are, this is a platform, a merry-go-round, for example, that is rotating at angular velocity omega. And if you are in this point, you will have a certain tangential velocity. If this mass is moving in another point, you have a bigger tangential velocity. Since there is really not something that does this acceleration, whatever you feel is something, a fictitious force, that is a Coriolis force, that adjusts the things. So it accelerates in the other direction. So whenever you move out from your axis of rotation in a merry-go-round, you feel like something that lets you fall on one side. And so if we move joint 1 of velocity q1 and we move joint 2, we see that this mass, for example, is moving linearly in this direction, and we have a Coriolis force. But as we said, both joint needs to be moving. If joint 1 is not moving, there is no rotation. So even if you move joint 2, there is no Coriolis force. And if you don't move joint 2, it means that everything is always at the same distance from the rotation axis. And again, you don't have any Coriolis force for whatever joint 1 velocity you have. And the important thing is that the Coriolis force affects only joint 1, because the mass of joint 2 is not moving with respect to the frame 2 origin. So you need a motion of the mass with respect to the frame you are computing the effect of the Coriolis force. And we said that we need a linear velocity, and joint 2, mass 2 is moving with respect to the frame 2 origin with a pure rotational motion. There is no linear motion. So the Coriolis force is only felt by the joint 1. And wrapping up everything, whatever we said, we have this. We have a Coriolis only on joint 1, and the dependency both on joint velocities. Sorry, this is the S matrix. So you remember you need to multiply this S matrix from the velocity. And in here we'll have a mixed term, Q2 dot, Q1 dot, and here we'll have Q1 dot, Q2 dot, and you have dependency on the position of link 2. And here you will see that you have only the squared dependency on Q2 dot squared and Q1 dot squared. And if you want to compute the Coriolis for this robot, you get these values. So you see that in essence, this matrix is dense, is not diagonal, and is dependent on what? Both on the position of Q2, but also on the velocity of Q1 and Q2. So it's dependent on Q and Q dot. And if you do the multiplication, you can get back whatever we try to say here in this qualitatively here, that you have the centrifugal term in joint 2 dependent on joint 1, and on joint 1 dependent on joint 2 motion, and the Coriolis are only on joint 1. Okay. Then if we put everything together, we get the final model that represents the dynamic model for a 2 degrees of freedom robot with rotational joints, where we have the inertia matrix, we have the Coriolis and centrifugal torques, that is the S matrix times Q1 dot and Q2 dot, and you have the gravity torques and the joint torques vector, which is on the right side. To summarize, this is the expression. We see here the M matrix as dependency on Q, as S matrix and G matrix. They are configuration dependent. And both the M matrix and the S matrix, they have couplings, they are dense. And these couplings, they show up in a peculiar way. So whenever you try to control one joint, you give a set point. For example, you're giving a constant set point to one joint, and you move the other joint, you will see that you have an influence on the first joint due to the inertial coupling that comes from the other joint. While the other way around, if you have a constant set point in the second joint and you do a step on the first joint, you will have a disturbance on the second joint. And as an example, if you want to play around, this is from the course of Osama Khatib. Is an example of 2 degrees of freedom robot, and you see that if you express the explicitly the two dynamic equations, two differential equations for joint 1 and joint 2, you see that you have the in red the influence of joint 1 on joint 2, joint 2 on joint 1. So this is the equation of joint 1, this is the equation of joint 2. In green, the influence of joint 1 on joint 2. Okay. Do you have any question on this? If not, let's do another 10-minute break. And we continue with the last part. This is a Newton-Euler approach to compute the dynamic model. Okay, let's continue. This last part is about the Newton-Euler method to compute the dynamic model of the robot. It's a method that is giving the same result as the Lagrangian one. But while the Lagrangian is good for analysis, and for example, I can set masses, and as we saw, we can compute the inertia and see the variation of inertia with the configuration. I can see the influence of each term. In this other approach, we are using classical mechanical equation, Newton and Euler equation, for rigid bodies. And we apply the balance of forces and torques and moments at each link. And we use the idea of recursion to propagate the acceleration using the moving frame ideas, whatever we use for the computation of the geometric Jacobian, to compute angular and linear velocity and accelerations along the structure of the robot till from the zero frame to the end effector. And then we do a backward recursion where we compute the forces and moments along the structure. And then we will see that we extract the torques at the joints in doing a projection. So instead of doing whatever we did for the Lagrangian approach, where we have the symbolic term, we plug in the values of parameters and we get the model. Here we have directly using this equation in a numerical fashion. So we get numerical evaluation of the model, and we get the equation directly in numerical form. And this method is better for example, inverse dynamics computation rather than forward dynamics computation. Because given a trajectory, we can compute, for example, easily the torque that produces motion in an efficient way. In addition to the joint torques, we said that we can compute the forces that are through the structure. So we can use this method also to evaluate the internal stress of doing a motion once we assign some values for the center of masses and the inertia parameters. And therefore can be used to select, for example, the material to be able to support, withstand some stress. And we start with the this is so the output is the same model that we get with the Lagrangian. And the Newton equation that we are gonna use. So first we consider the single link, single rigid body. And we want to write the Newton equation for this rigid body. We look at the mass and all the forces acting on this mass. And we can say, according to Newton, that the sum of these forces is equal to the variation of what? Of its linear momentum. Since the mass is constant, we take out from the derivative and we get mvci dot that is the usual form of the Newton law. We use this formulation because we will see that it will make sense in the angular case. So we have joint I axis, ZI, joint I plus 1, axis ZI plus 1. We have the center of mass of link I. We have the gravity that is acting at the center of mass of link I. And we have what? We have a force coming from link I minus 1. So this is the force that link I minus 1 applies on link I. And we have Fi plus 1 as the force that the link I applies on the link I plus 1, on the following one. So these are the interaction with the previous and following links in the structure of the robot. We have also the tensor of inertia of the link with respect to the center of mass of link I. All the vector should be expressed in the same frame. We choose arbitrarily the world frame, an inertial frame fixed. Okay, then if we write this expression that we wrote, we have Fi coming from the previous link. Then we have a principle of action-reaction, you remember. Since Fi plus 1 is the force of link I that link I is doing on link I plus 1, if we want to do the force balance for link I, we need to consider the minus I plus 1, the minus sign on the force coming, that link I plus 1 is, link I is doing on link I plus 1. And this sum of forces is equal to the variation, and so, sorry, we are also missing a gravity force, and this sum of forces is equal to the variation of linear momentum, that is m time acceleration of the center of mass of link I. Then, now the thing get complex if we, linear acceleration of the central mass of link I. If we move to the angular motion of a rigid body, the equation that describes the balance of moments for the rotational motion of a rigid body is the Euler equation. And because we are talking about moments, we need to be very careful, and we need to define what is the pole with respect to which we compute the moment and the tensor of inertia. And as a pole, we arbitrarily select the center of mass. On top of this, as before, we need to decide what is the frame where we express our vectors. And again, arbitrarily, we select this frame is the world frame. Then the Euler equation, it's the one that links the sum, says that the sum of the moment applied to the rigid body is equal to the variation in time of what? Of not the linear momentum, but of the angular momentum, which is the tensor of inertia times omega. Okay, I said that everything is expressed in the warframe, so I don't write any subscript. I give them for implicit. Then, if we work out the derivative of the product, we get ICOM omega dot plus, also we know that the tensor of inertia can vary if we express in an inertial frame, because depends on the orientation, remember, of the link. So we can do this time. We can consider explicitly the rotation matrix that maps the link I-frame into warframe, define the constant tensor of inertia in the I-frame, in the link frame, and use the transpose. Okay? And this is times omega, the second term. Now if we develop this, we get again ICOM omega dot plus, we do the derivative. I don't express this subscript just for sake of simplicity. Derivative of R times ICOM, I do it here, times R transpose plus R ICOM, that is constant. I don't differentiate because it's in the link frame, and we said that in a link frame the inertia tensor is constant, times R dot transpose. Now copy this, we replace R dot with omega cross R, we have the constant tensor of inertia in the link frame, and we have sorry, this is missing omega. And we have R transpose omega plus R and this is R dot transpose is R transpose omega cross transpose times omega again. So we just split this sum, distribute on multiplication on omega. And if we look at this term, we get back to the ICOM one. And this term is what? This one is minus omega cross. And we get something like minus omega cross. If we go back to the cross product, we get something omega cross omega. These are parallel vector because they're multiplying same thing vector for itself, and the cross product is 0. So all this term goes to 0. And we remain with just this part, ICOM omega dot plus, again we go back to the cross product from the symmetric matrix, omega cross ICOM omega. And this is the Euler equation. Very simple, where this is the inertia of link I with respect to the center of mass expressed in warframe. So, and this term is called gyroscopic effect. Okay, if you launch a pen in the air, you see that this pen starts to rotate. Okay, and this rotation is as likely due to the term omega cross I omega. Why? Because the momentum, the angular momentum, whenever the pen is in the air, since there are no external moment, conserves, so is equal to 0, the sum of the moments. So we get ICOM omega dot equal to minus omega cross I omega. And this is exactly whatever makes the pen rotate around some axis and wobbling. If you put a sphere that has a perfectly diagonal inertia matrix, what happens is that if you multiply for omega, you get omega cross, and you have same element on the diagonal, then you get omega cross omega, and you get this term goes to 0. In fact, a sphere, if you launch it in the air, if it's perfectly symmetric, doesn't rotate. Now, we can put everything together, and we need to understand what are the moments that are applied on the body. So we have a pure torque, pure moment transmitted from link MI, transmitted from link I-1 on link I. We have the moment that the link I exerts on link I+1, so will need to be accounted with the minus term. Plus, we have what? We have other moments, right? They are the ones due to the external forces. Sorry, to the interaction forces with the other links, Fi and Fi+1. Since we are choosing the center of mass as pole to compute the moment balance, the gravity force will have no moment, so we don't consider that. And we consider the cross product between the, to compute the moment of Fi, the cross product of P, C, I, the vector from center of mass to application point of Fi, and the moment of this force will be this. Plus, what? The moment of the force Fi+1 that will need to be accounted with a negative sign. This is the vector between center of mass and application point of Fi+1, and Fi+1 we consider with negative sign. And then this is equal to what? Whatever we wrote before, where we consider the inertia at the center of mass of link I and omega I, the angular velocity of link I. Now that we have these two equations that allows us to compute the balance for each rigid body of torques and forces, we use this recursion idea that, in essence, tell us to first propagate velocities and acceleration from the base frame to the end effector through forward kinematics. And we can use to do so the recursive formalisms with moving frames that we used for geometric computation of the geometric Jacobian. So we start from the base frame. We have an initial velocity in the base frame, we an acceleration. We transmit this to the next body. We apply the joint acceleration, and we compute this velocity and acceleration for the next link. Then we do apply the second joint contribution, and so till the end. Then we have the backward pass that does the opposite. Once he work out all the accelerations for the links, it goes back and compute starting from the end effector. So if you have any force or moment applied to the end effector, you need to count it here. Go back to the base using what the Newton-Euler equation that we computed. That allows you to relate now the forces at joint I to the forces and moment at joint I plus 1. Sorry, relate the forces and moment at link I to the forces and moment at link I plus 1. Once we have all these 3D forces and 3D moments, which is a 6D vector, we can project along the axis of the supporting joint and get the torque or the force if it is a prismatic joint. So for example, for the acceleration recursion, you know, we do this example for just the prismatic, the revolute joint, and you can find in the Sicilian book the version for the prismatic joint. So you know the expression that relates the omega, the angular velocity at link I, to the angular velocity of the previous link, and this is the joint contribution along the joint axis. Then if you differentiate this, you in essence get this expression where you do the derivative of this, and you do since Zi is moving, you know, is in a moving frame, you need to consider the cross product with omega I. And for the velocity, linear velocity, we have for revolute joints this expression that you can find in slide 23 at the lecture on differential kinematics. And if you differentiate this, you get this expression. So this is the time derivative of this, and the time derivative of this term is doing first the time derivative of this times the other one, plus the fact that this vector is in a rotating body, so you need to consider the omega cross the vector to compute the derivative of rotating frame. And the same whenever you have the acceleration of link I origin, you can get in a similar way the acceleration of center of mass of link I. So this is for what regards the forward pass, which is the acceleration recursion. And you do for one link, you propagate, you need to start initializing the algorithm with the initial the angular velocity of frame 0, the angular acceleration of frame 0, the linear velocity of frame 0, and the linear acceleration of frame 0. And if you compute the gravity, put the gravity here, because the gravity you apply as an acceleration at frame 0, you will see that you can avoid to compute them, account for gravity in the Newton equation. So in the previous equation that we said gravity was here, you can remove that in the computation. Okay, now backward recursion. So we start from the last link, and we go back by recursion, computing the moment and forces for link I, starting from the moment of force of link coming from link I plus 1, and from the moment coming from link I plus 1, and we just use in here the Newton equation. We previously computed this from the forward recursion. We know also from forward kinematics the position of the center of masses. This we computed here, and we know again from the forward recursion the accelerations and the angular velocities. So we have everything. We can compute this for each link, and then we project along the joint axis. In the case of prismatic joints, we project the forces, 3D forces, while in case of revolute joints, we project along the moments along the joint axis. And we know that this tau I is a scalar, but here we have 3D vector and 3D vector. So we have 5D informations that we represent something. What do they represent? They represent what we call the internal forces transmitted through the structure from one link to the other. So you know that there are these, remember the generalized coordinate definition, the joint allows only one motion, and all the other forces that are in other direction that the motion that is allowed are internal forces that go through the structure. Then to summarize, we have as input the initial velocity, angular velocity, angular acceleration, of frame 0, and linear acceleration, angular acceleration of frame 0, and which is the base link. We can provide the direction of the gravity, and we also need the position, velocity, and acceleration of the joints that allows us to compute the forward kinematics. And then from the last link, if we have any contact with the environment, we need the terminal condition, we need the force and moment at the end effector or at the last link. Then by forward recursion, using all this data, we can compute the angular velocity, angular acceleration, linear velocity, and linear acceleration for each link, and in the case of linear acceleration and velocity for the center of masses, and do the backward recursion starting from the last and the factor force and moment, compute the force and moments for each link, and then project through the axis and get the torques. So given the model of the robot and that give us the masses, kinematic parameters, and the trajectory of the joints, using this we can, for example, compute the joint torque. So we can perform inverse dynamics and compute the inverse dynamics torque to realize the motion, a desired motion. And this is the main application of this algorithm, Newton-Euler algorithm. To summarize whatever we said, we have the forward recursion of the acceleration for all the joints, computes the angular velocity and angular acceleration and linear acceleration for all the joints, and then goes back with the backward pass, propagating the forces and torques, forces and moments. These are what we call and with a projection, we can compute the torques at the joints. To comment about this, the advantages of this Newton-Euler, recursive Newton-Euler algorithm are that is in numeric form, not in symbolic form. And the advantage is that the computational complexity that is linear with the number of joints. Think about each step, the propagation, the recursion, forward or backward remains the same, it doesn't become more complex. So the computational complexity is linear because if you double the number of joints, we will have double the number of the same operation of propagation. So there is no increase in complexity, while the Lagrangian approach explodes for a very few amount of joints, and it's combinatorial. It becomes exponential complexity, I think. So the Newton-Euler is recommended, especially for real-time application or whenever you have a big number of joints, and it works, of course, for any kind of robot, given the kinematic and dynamic quantities. This is the model that you can extract. You saw from the CAD last lecture, or from identification procedures. Then, as a possible use of this algorithm, as we said, the main one is to compute inverse dynamics torques. How do we do that? We will see this in the lab session. We call the algorithm with 4 parameters. One is the gravity vector that we provide, and the other ones are the position of the joint, velocity of the joints, and acceleration of the joints. So we see that in inverse dynamics or in computed torque, we use the desired values. In inverse dynamics, we only use the actual values for the velocity and positions. We will see that, while we always use the desired values for the accelerations. And if you call the algorithm with this, we get out this, that are the torque necessary to perform the motion represented by Q dot and Q dot desired. So but you might want to compute this term separately. So there are some tricks to get the gravity terms. You, in essence, provide the gravity vector, of course, and put zeros for Q dot and Q dot dot. So if you put 0 for Q dot dot, you nullify this term. And if you put 0 for Q dot, you nullify the centrifugal term and remain with only the gravitational torque. While if you want only the centrifugal and Coriolis, instead you put 0 to the gravity vector, so it won't compute the gravity forces, and you put both Q and Q dot and no acceleration. Unfortunately, you cannot compute the matrix S. You can only compute with Newton-Euler, you compute only the vector of Coriolis forces, so an n vector and dimensional vector. You cannot split into the C matrix. While you can still do something for the inertia matrix. And the trick here is that you can compute the inertia matrix by computing each column separately. So if you call the algorithm with 0 gravity, position of the joints, 0 velocity of the joints, you don't have Coriolis and gravity, and you can select, if you set one acceleration with a vector EI with a 1 in correspondence of the joint relative to the column of the inertia matrix you want to compute, you will compute only the ith column of the inertia matrix. And of course, you need to repeat for all the joints. So you do first for this joint, then you do for this other joint, then you do for the third one, etc. Finally, there is something that you can do, people do for collision detection. They use the generalized momentum, which is the product of the inertia matrix times the joint velocities. And in here, the trick is to just use the no gravity, position of the joints, no velocity, and put velocity instead of acceleration, and you get only this term of the model. And this is used for collision detection without having sensors. So whenever you have an impact on the robot, you can check this generalized momentum and you will detect a collision. This is an algorithm invented by Alessandro De Luca. As an example, we consider again a planar robot with 2 degrees of freedom. First link is 10 kilogram, second link is 5 kilogram. The first joint goes from 90 degree to 0, so does a motion like this, while the second one goes from minus 180 degrees to 90. And if you look at stroboscopic view, the first the robot is folded like this, and then as is going, the first joint is going down like this, the second one is opening this way, and the final configuration is this one. So we can set a polynomial, quintic polynomial trajectory to define this motion. A polynomial, quintic polynomial allows us to set either both the initial and final acceleration and initial and final velocity. So we set them to 0 both at the beginning and at the end. And we consider gravity, so we are on a vertical plane. And if we do the plot, we achieve, for the trajectories, we have these plots. So this is for the first joint that goes from 90 degrees to back to 0. And while the second one is going from minus 180 to 90. And we see that this is the quintic for position becomes a quartic for velocity and a cubic curve for the acceleration. But initial acceleration, final acceleration is 0, initial velocity, final velocity is 0, both for the first joint and for the second joint. And if you look at the torque, at the various contribution of the torques, we can have many conclusions. We have, this is the total torque at joint 1, and at the initial point the torque is 0 because we have initial 0 velocity and 0 acceleration, and the initial config, remember, is the one that for which the gravity torque is 0, because the robot is folded like this, and its gravity forces are going through the joint axis. So everything is 0. Then if the robot is moving at the final configuration, we have 0 acceleration and 0 velocity. So if we see, the blue one are the inertial terms that are 0 both at the beginning and at the end. The purple one are the gravity forces, and we see that at the final configuration, which is this one, we have the second joint that has doesn't have to withstand any gravity because the gravity goes through the joint axis, while the first joint, which is here, needs to apply a torque, a positive torque, to withstand the weight of the first and the second link. And blue are the inertial, and the Coriolis and centrifugal are green, and they, because of velocity 0 at the beginning and at the end, they are going to 0 at the beginning and at the end. And at the beginning, you can see that the main contribution to the torque is due to the inertial torque, because the velocity is very small and the system is accelerating a lot at the beginning while the velocity is still low. So to achieve to do these plots, we need to do the following. We compute the bias terms, both the Coriolis and the gravity term in the way that I showed you before. We compute so this way we can use, and these are called also nonlinear effect. So the sum of gravity and Coriolis. We compute inertia matrix, and so we are doing for each column. So this is complexity, linear complexity, because we do one forward pass and backward pass. Then we have quadratic complexity, because we need to do for each column, for n column, for the computation of the inertia matrix. And then we compute using this and this. We compute the accelerations of the joints, doing the inverse of the inertia matrix, and given the torques that we apply. So this is, sorry, didn't say, this is for the forward dynamics. So we have torques as input and acceleration as output. So these are the input torque, and this is a motion we want to get out. And we get for the inversion of the inertia matrix something that is cubic complexity. So this is the reason for which we don't want to use Newton-Euler to compute the forward dynamics, the direct dynamics, but there are better algorithms that are the ABA, the articulated body algorithm, that remains linear in the complexity, and it doesn't get inefficient, while the Newton-Euler becomes inefficient for forward dynamics. Therefore, we use only for the inverse dynamics in general. If you want to do that, use for forward dynamics, once you get the acceleration, you need to integrate. Remember to integrate the acceleration with an integration algorithm that could be, for example, forward Euler or Runge-Kutta 4. And from this, you get joint velocity and positions, and then you iterate for each loop, and you get the motion out of the torques. So I would close here. I will quickly detail tomorrow how can we implement forward Euler integration method, which is the simplest one. Just if you want to implement your simulator, you can do that. We will see, we do that in the lab following this approach. So unless you don't have questions, I'll see you tomorrow. And tomorrow is the last lecture on dynamics. Then the next week, Octavio will introduce the final part that is on control of the whole robot, using the dynamics and kinematics. We put everything together in a sense. Good evening, everybody.